On June 11, 1980, St. Lucie Unit 1, a combustion engineering-designed pressurized water reactor located in Florida, experienced a reactor trip from full power. A reactor trip is a standard designed safety response. Control rods insert, fission stops, and the primary focus shifts to removing residual decay heat. Under normal circumstances, this is a routine operation carried out by massive reactor coolant pumps forced circulating tons of water through the core every minute. However, in this case, the cause of the reactor trip was loss of cooling to the reactor coolant pumps. Operators had to shut down the pumps to avoid overheating the pump seals. Without the pumps, the operators were facing a much more complex scenario: a natural circulation cooldown. This is the story of the hidden bubble, St. Lucie's Natural Circulation Challenge, a significant operational event that would have industry-wide implications for procedures, training, and actual nuclear plant hardware. To understand the St. Lucie event, we first need to look at the architecture of a pressurized water reactor. The system must remain highly pressurized, around 2250 psi, to prevent the coolant from boiling, even at temperatures exceeding 600 degrees Fahrenheit. Control of this pressure falls to a single component, the pressurizer. Think of it as a surge tank. It holds a steam bubble at the very top of the system to absorb pressure changes, acting as the spring against which the entire reactor coolant system pushes. Heat generated in the core is transferred to the primary coolant, which flows to the steam generators. These giant heat exchangers transfer that energy to a secondary loop, boiling water there to generate steam for electricity. This transfer is the primary way to remove heat from the core and prevent the nuclear fuel from overheating. After exiting the steam generator, the cooled fluid is pumped back into the reactor vessel by the reactor coolant pumps. The mechanical seals in these pumps that separate the motor from the radioactive fluid require constant active cooling. Without it, the seals could fail in as little as 10 minutes, creating a path for a loss of coolant accident. The initiating event for this scenario was a valve in the component cooling system failing closed due to a nearby steam leak. This instantly cut off cooling to all reactor coolant pumps. Procedures allowed the pumps to run for only 10 minutes without cooling. When operators couldn't fix the valve in time, they were forced to trip the pumps and shut down the reactor to save the seals. With the control rods inserted, the fission chain reaction stopped, but the decay heat from fission products continued generating roughly 6% of full power, massive energy that still had to be removed. Without pumps to force circulation, operators had to rely on natural circulation. This relies on thermal physics. Hot, less dense water rises from the core to the steam generators, cools, becomes denser, and gravity feeds back down. It is effective, but it is a delicate, slow process. Crucially, natural circulation flows well through the loops, but barely moves water through the top of the reactor vessel. The crew's objective was to bring the plant to cold shutdown, which requires lowering both temperature and pressure. At the time, procedures allowed a cool-down rate of 100 degrees Fahrenheit per hour. Operators followed this rule perfectly. However, because the flow in the vessel head was stagnant, it stayed hot while the rest of the system cooled. By following the procedure, the operators lowered the pressure below the boiling point of that hot, trapped water, forming a large steam bubble, effectively a second pressurizer, in the reactor vessel head region. To visualize exactly how this void formed, we need to look at the saturation curve. This line is the physical boundary between water and steam. To the left and above the line, water remains a liquid. Below and to the right, it boils into steam. When operating at full power, the primary loop of the reactor is at approximately 2250 psi, and the hot leg of the reactor is around 585 degrees Fahrenheit. In a pressurized water reactor, our golden rule is to stay in this top left zone, the subcooled region. When placing the reactor in cold shutdown mode following a reactor trip, we need to lower the pressure and temperature together, carefully staying away from that boiling line. As the cool down begins, watch the two dots. The yellow RV dot represents the water flowing through the pipes and steam generators via natural circulation. It behaves perfectly. As the operators cool the plant, its temperature drops rapidly, and as they depressurize, it stays safely deep inside the liquid zone. But look at the red vessel head dot. Because the water in the head is stagnant and trapped inside that massive steel dome, it isn't cooling as quickly. Its temperature remains stubbornly high. However, since the whole system is connected, its pressure is dropping just as fast as the main loop. At approximately 980 psi, the head path crashes into the saturation line. The water in the dome can no longer exist as a liquid. It begins to flash to steam. By the time the system reaches 800 psi, we have a massive disparity. The main loop is sitting at a comfortable 345 degrees Fahrenheit, well below boiling. But the vessel head is still radiating heat at 536 degrees. At 800 psi, water boils at 520 degrees. That 536-degree heat is instantly converting the water into a steam bubble, displacing fluid and confusing the control room's level indications. At the time of this event, pressurized water reactors did not have temperature indication in the reactor vessel head region. As a result, the operators were unable to detect this temperature divergence before the vessel head steam bubble formed. The most disorienting symptom for the operators was the erratic behavior of the pressurizer level. It began to oscillate in a jagged, sawtooth pattern, rising and falling in ways that defied standard hydraulic logic. This happened because the plant effectively now had two pressurizers fighting for control: the actual pressurizer, which the operators could control, and the void in the reactor head, which they could not. Here is the hydraulic loop that trapped the operators. We have the reactor vessel on the left with stagnant hot water in the head and the pressurizer on the right. Watch the relationship between the spray, the pressure, and the hidden steam bubble. The cycle begins when the operator initiates auxiliary spray to lower system pressure. As the cool water condenses steam in the pressurizer, the system pressure drops, just as intended. But once that pressure drops below the saturation point of the hot head, the water flashes to steam. This expanding steam bubble acts like a piston. It displaces liquid from the vessel, driving it through the hot leg and straight up into the pressurizer. The operator sees the pressurizer level spike rapidly upward. This is the two-pressurizer phenomenon in action. The bubble in the head is growing, forcing water into the pressurizer tank. Reacting to the high level, the operator cuts the spray and energizes heaters. Without the condensing spray, the system pressure begins to recover and rise. As pressure rises above saturation, the steam bubble in the head is crushed back into liquid. The piston retracts. Water is sucked out of the pressurizer to refill the void in the vessel head, causing the indicated pressurizer level to crash back down. and the cycle repeats. Spraying to lower pressure creates a bubble that raises level. Stopping the spray collapses the bubble and drops the level. This push and pull created the signature sawtooth pattern that baffled the control room. This creates a deadly cognitive trap. Operators are conditioned to trust the pressurizer level as their fuel gauge. A high level means the tank is full. The standard drilled response to a high level is to stop adding water and increase letdown, draining coolant from the system. But in a voiding scenario, a high level is a lie. If the St. Lucie operators had followed that indication and drained the system, they would have removed vital coolant inventory. The bubble in the head would have grown larger to fill the space, potentially pushing down far enough to interrupt natural circulation or uncover the core. And this is where the shadow of 3 Mile Island falls over the event. Just 1 year prior, in 1979, the operators at TMI faced a similar phantom. A stuck-open pressurizer relief valve caused a small break loss of coolant accident. As reactor coolant inventory was lost through the valve, voiding and flashing occurred elsewhere in the system, producing a misleading rise in pressurizer level due to thermal expansion effects. Operators, trained to treat high pressurizer level as evidence of an overfilled system and to avoid going solid, reduced emergency core cooling flow. With the relief valve still leaking, net coolant loss continued, leading to core uncovery and partial meltdown. Fortunately, the St. Lucie crew recognized the discrepancy. They realized the sawtooth level changes were a signature of a void, not a true inventory excess. They resisted the urge to drain the system, accepted the high level indication, and focused on slowly collapsing the bubble by stabilizing pressure. They avoided the trap that had claimed Unit 2 at 3 Mile Island. Once the crew recognized that aggressive depressurization was driving abnormal pressurizer behavior consistent with voiding, the solution became an exercise in patience. Operators avoided further rapid pressure reductions that would increase flashing. Instead, they used much slower cooldown rates and hold steps so the upper head fluid could equilibrate thermally with the rest of the RCS. Slower depressurization reduces the tendency for isolated hot pockets to flash as saturation falls. With these conservative control actions, the operators maintained overall core cooling and eventually achieved normal shutdown cooling conditions without a loss of core cooling. As a direct result of St. Lucie and the lessons from TMI, the NRC issued Generic Letter 8121, which required licensees to evaluate their ability to prevent, detect, and eliminate reactor vessel head voiding. Through this process, and reinforced by the TMI Action Plan, PWRs were required to provide positive reactor vessel head venting capability, leading to the installation or upgrade of remotely operated head vents. Now, if a void forms, operators don't have to guess. They can open the vent, bleed the steam to containment or the pressurizer, and refill the head with water, maintaining positive control of the system volume. The St. Lucie cooldown event serves as a critical case study in the limits of procedures. The crew did not panic. They did not violate their license. In fact, they were following their instructions to the letter, cooling down expeditiously to protect the reactor coolant pump seals. But their procedure had a blind spot. It assumed the entire reactor was one uniform temperature, failing to account for the unique geometry of the vessel head. It teaches us that in complex, high-energy systems, you can follow the rules and still end up in a corner. It highlights the importance of operator fundamentals, the ability to look past the procedure step in front of you and visualize the physical reality of the machine you are operating. St. Lucie reminds us that progress in nuclear safety is often incremental, built on careful observation, humility, and learning. The event revealed subtle plant behaviors, corrected hidden assumptions, and led to lasting improvements in PWR design and operation. We are fortunate that these lessons were learned with core cooling maintained, allowing safety to advance through insight rather than consequence.